For here, we give an application of orthonormal bases. Now, if we're willing to go to the trouble to find an orthonormal basis, there's some nice formulas that come out. In fact, you can think of these formulas as being finite dimensional analogs of the formulas that are used in the analysis of Fourier series. For myself, I learned Fourier series before I took linear algebra, so those formulas were pretty unmotivated. Now, the problem, first I'm going to have three vectors in R3, v1, v2, and v3. We want to verify that they form an orthonormal basis of R3. Then, I'm going to take the vector 1, 2, 2. I want to express 1, 2, 2 as a linear combination of the vectors in our basis. Finally, we're going to take the length squared of 1, 2, 2, and I want to show that's equal to the sum of the squares of the c's that occur in our linear combination. Now, for the first part, okay, this is the basis that I want to work with. So we just want to check that it's an orthonormal basis. Now that means if we take any two of these vectors, distinct, take their inner product, we get 0. If we take the length of any of these vectors, we get 1. So this just says our vectors are mutually orthogonal and they're unit vectors. So one way to show that we have an orthonormal basis, we take our vectors, we load them as the columns of a matrix A, then we compute either A transpose or A transpose A. We expect to get the identity matrix out if we have an orthonormal basis. So this is just a compact way of writing out these equations here. Now, this is just a matrix multiplication, so I'll leave it to you to see that we get the identity. Now, Fourier's trick is a quick way to get the coefficients from a linear combination. The only catch, we need to have an orthonormal basis. So, recall, the usual way I would go about finding the coefficients for a linear combination given a basis. Take our basis vectors, load them as the column vectors for the first part of an augmented matrix. We take the vector that we're interested in, load it as the last column, and then we start doing Gaussian elimination. For Fourier's trick, if I want to get these coefficients and I have an orthonormal basis, the ith coefficient I get by just taking our vector v, inner product with our ith basis vector. Now, to see why that works, let's see how we would get C1. So I take inner product of v with v1. I can expand v as C1 v1 plus C2 v2 plus C3 v3. That's against v1. We could use bilinearity to break up our sum. And then because we have an orthonormal basis, okay, v1 with itself goes to 1, v1 with v2 or with v3 goes to 0. So this term right here collapses down to C1. Now, with our example, so I'm going to take 1, 2, 2, and then take the inner product with each of our basis vectors. So what comes out, get minus 1 over square root of 2, 5 over square root of 3, and minus 1 over square root of 6. Of course, we check our work. So I'm going to take the linear combination that goes with these three numbers. We expect to get 1, 2, 2 when we work things out. And we notice when we get to this step and crunch things down, we check our work. Finally, we have Parseval's identity. This will give us a way to relate the norm squared of our vector to the coefficients coming from the linear combination. Again, this only works when we have an orthonormal basis. Now, Parseval's identity is striking when we come across it in Fourier analysis. We can use that to show that the sum of the series for 1 over n squared is equal to pi squared over 6. Okay, that's not obvious by looking at it. Now, in our specific example, if we take the norm squared of 1, 2, 2, we get 1 plus 4 plus 4, which is equal to 9. If we take the sum of the squares of the coefficients from the linear combination, we have a half plus 25 thirds plus 1/6, which gives us 54 over 6, which is equal to 9. And that verifies Parseval's identity in this case. Now, to see why Parseval's identity is true, let's consider the norm squared of our vector v. So that's given by the inner product of v with itself. In the second slot, I'm going to expand v as the linear combination. And then I can use bilinearity to break this up into a sum. Now, the inner product of v with v1 is the definition of c1. The inner product of v with v2 is the definition of c2. And the inner product of v with v3 is the definition of c3. So what comes out is going to be c1 squared plus c2 squared plus c3 squared. And that gives us Parseval's identity.